Now we are moving on to multiple loops. So we started with a straight line. Then we bent the line and we saw what happens. Now we're taking this bend, but we are taking to the next level. A lot of them. A solenoid is a coil of insulated wire wound closely in the form of a helix. So that is your solenoid. Let me show it actually. Let me show this. So I have it here for you guys. That's your solenoid. So that's I'm doing something with the solenoid over there. But anyways, so in this video, we're looking at some introductory aspect of solenoid. So you can get 1 mark or 2 marker. We need to know this, and for derivations also we need to know this. So we need to know that anything with X is going or coming out, sorry. This is coming out and this is going in, correct? Nope, this is, sorry, going. This is going in and this is coming out. This we need to know, and that's your solenoid. And what else? Helix is nothing but a spring shape. Okay, so that's that. Now we need to know about the magnetic field pattern that a solenoid creates. So the field inside the coil is nearly uniform. That fact we need to know. And they are parallel lines running from north to south. So within the solenoid will be from south to north. Okay, I don't know if I made that. Wait, consisting of parallel lines running from north pole to south pole, that is outside. Inside it is south to north actually. South to north. One at each end of the solenoid. Okay, I didn't get the statement. Sorry, let me read it again. The field inside the coil is nearly uniform and consists of parallel lines running from south pole to north pole, one at each end of the solenoid. Okay, so basically this is say north and this is south. So at the ends, that's what it means. The strength of the field depends on the number of turns, amount of current flowing through, so on and so forth. Now we have to actually look at drawing this. So what does this mean? Current is going in. This is current is coming out. So basically we'll look at this. So our magnetic field lines will be inward. Why is it inward and all of that? How to determine that? That will be having a discussion. Okay, something like that. So why is it so? I mean, not why. What is the pattern? And how do you determine this? That's something that we'll learn. Why is it so is not an easy thing to discuss actually. So what I'm doing, I'm trying to keep it straight in the middle. And everywhere else a bit bent. So it's almost straight, right? And over here, so we say we have over here, it's like this and something like this. Here too. Don't waste your time doing this detailed version. I mean, this is not detailed version actually. Okay, this is good enough, right? Be mindful of your direction. So it would be so, and north it would be so. And over here, it would be, it's outside. So it is from north to south. Okay, don't do this actually. That is wrong. That's right. I think that's good enough. That will be your just basic patterns. Just draw this. Don't worry about the neatness and everything. This is the best you can do within the given time. Now outside the field is weaker, right? The field line diverges with increasing distance from the solenoid, that we can see in the diagram also. It moves out. That's common sense. When we reverse the current, the north and south both of the solenoid will flip. So that too I haven't actually, I have done the experiment. Let me show that. Okay, I have it here. So now it's switched off. We can see the north, that's your solenoid. And now when we have negative current, okay, so yeah, now. So you can see the deflection is pretty huge. Actually, it was, remember, to the right. And the red thing, now it is to the leftish almost. Okay. Left to us, that is. To itself, it turned right. Now I switched off the current, so it's back to pointing towards the north. And when we have the positive current flowing, and we have it to be flipping in the other direction. So I'm sure you guys know this. So now in detail, why is this happening? So it can be explained with the help of principle of superposition. The net magnetic field at any point due to multiple source is the vector sum of the magnetic field produced by each individual source. So basically what we're trying to tell is each loop will contribute to the entire effect. That's it. That's a simple language. Again, you can get anything anywhere. I'm just listing out all the possible things. Magnetic field in a solenoid. So the magnetic field at any point in the is sorry. Let me read it again. The magnetic field at any point is the result of the combined magnetic field produced by all the loops of the coil. So actually, sorry, this is the same point. Now, direction with the Ampere's right hand rule. This is what I wanted to discuss. So if I see a current going, say this is, sorry, this is upper, this is niche. And here we have this to be niche and this is going down. So basically, if I take up the right hand, okay, curl your finger in such a way that it's pointing in the direction of the current, then the thumb will be so, right? Do that with your hand. Do this. With your right hand, do this. So this is your direction of the current in the loop. This is your direction of current in the loop. And your thumb will point in the direction of north. So this end is north and this end is south. The thumb will point in the direction of the magnetic north pole. Okay, so that's how you can figure out. So yeah, I think there's nothing much. Yeah, this is a small introduction. So you can pause, recall what is solenoid, and based on this, we'll learn few things. Learn to draw.